So these kind of things give us a really easy way, because it doesn't take too much time, to figure out all kinds of answers like this. As long as we have some kind of initial amount, and we know after some amount of time how much there is, we can figure out these kind of questions. We can figure out how long it's going to take to reach a certain amount, or the other way around. Figure out how much time it would take to reach a certain amount, or to figure out after how much time we're going to have. So those were both growth models. Next one we're going to look at is untitled decay, which I kind of mentioned to begin with. It's the same thing, except for this time your constant is just negative. But they're going to work the exact same, just different context. Instead of something growing, it's something decaying. In any other classes other than math classes, have you ever talked about anything that has exponential decay or untitled decay? About your science classes? We'll see if this looks familiar then. Probably. Talk about anything that was radioactive ever, like a whole bunch of the elements there at the bottom are all radioactive. I'll kind of explain how that works a little bit in this one. Again, don't get freaked out because you don't really understand the context at this point. It's really not that bad. And the math work is exactly like what we've been doing. The only difference is now K is naked. All right, so this one, I'm talking about radioactive decay. I kind of put a model up there just to kind of show you how this works. The one that we're talking about is iodine, and that model is not specifically for iodine, but it kind of shows you how radioactive things work. It's a fairly simple concept, as in if you've got something that's radioactive, it's not very stable. As in, like most atoms, the protons, the neutrons, the electrons, they stay the way they should. With radioactive stuff, it's not very stable at all. It's something that over time, it breaks down. And when it breaks down, what happens is a couple things get released. Particles are kind of flying off this. Like whether it's a neutron, proton, electron, things that should be there are coming off. And when they come off, energy is also released. And that energy is, what's it say? Underneath it? Radiation. So if you think about like the reactors in Japan, this kind of stuff's happening right now. In their reactors, whether it be plutonium or whatever they use this kind of process to produce energy. But right now, it's being released in a way that's not necessarily contained. So when that energy gets released, that radiation is being released. And then it can get absorbed by people, plants, animals, all that stuff, and it has a pretty bad effect on it. In this case, we're talking about iodine-131. So it's a radioactive material that decays according to that function. So the amount that's left after this time equals the initial amount times e to the negative 0.0817. And then we're going to assume that our scientist has a sample of 100 grains. So that's our initial amount. First question. What is the rate of decay? What is the rate of decay? So just look at it. What percent is this decaying by? Okay. Negative What percent would that be? Negative 8.7%. In this case, it's a good question. In days, so let's add that to it. T is in days. Next thing, just like the other one, I want you to graph the model. Okay, so type that in. When you type it in, what are you going to plug in for A sub 0? What's the initial amount here? 500. So you're going to type in 500 times E, just everything else. Sorry, 100. My mistake. So we're going to do Y equals 100 times E to the negative 0.087 T. Or when you type it in, you'll have the X there. Now again, we're going to play with the window sum. What I know, the highest point it's going to be at is 0. So go to your, you already have it typed in. Go to your window. X min, that can be 0. X max, why don't you make that 25. Your X scale can stay 1. Your Y min can also stay 0. And your Y max can be like 100 or so. Yeah, right. So but it's not going to go above it at all. But yeah, as long as you've got at least 100, you can go higher. There's nothing wrong with that. That's right, graph with that scale. Then when you do that, you can see the curve pretty well. Like when we look at these exponential functions to begin with, if we've got a negative exponent, it's going down, which makes sense because it's decaying. The mass is getting smaller. So it's going to start up here at 100 and then just kind of curve down like that. And what's it getting closer and closer to, but never really going to get to? So it's never going to completely disappear. There's always going to be some mass left to it. And eventually it'll be such an insignificant amount that we'll barely be able to detect. We graphed it. Next question. Part C. How much is left after 9 days? So how much of this material, out of the initial 100 grams, is left after it's been sitting there for 9 days? So what are we going to do to figure that out? Plug in 9 for T, so purely a calculator problem at this point. We're going to do 100 times E to the negative 0.087 times 9 power. So the nearest tenth of a gram, what do you see? Yep. About 45.7 grams. So after 9 days, over half of it had went away. All right, one last question. And something else, if you've had any chemistry classes in which you talked about radioactive stuff, you might have heard of this term. You ever heard of half-life before? What? No. Battery. Yeah. Yeah. What about radioactive stuff? Nobody's heard of half-life? Half-life is basically the time required for half of it to go away. that's something we kind of care about. Usually a lot of things have like a half-life number assigned to them. So like when they do carbon dating and those kind of things, that's what they use to figure that out, is the half-life. So all I want us to do here is, part D, what is iodine 131's half-life? Given the info that we've got, what is the half-life?
What's the 131?
What?
What's the 131?
In this case, that would be its atomic mass. Have you had chemistry before?
Yeah.
Like, you remember talking about isotopes ever? They were like ones that had like different amounts of neutrons. So this is the iodine version that has a total mass of 131. So like regular iodine is not regular. But iodine 131 has extra, I think it's just like one extra neutron. And that's what kind of throws everything off and makes it radioactive. So that's what the 131 stands for. So it's just basically the... All right, so we're going to figure that out. Any thoughts? How would we figure out what the half-life is? What? Put 50 in for A. You want to figure out when a half-life's going. So I'm going to do 50 equals 100 e to the negative 0.087 t, and then just solve that for t. Again, it's the same kind of work we've been doing. And I'm hoping by now, kind of like I was figuring, that this stuff's getting a little bit more clear. I know when we first covered these logarithms, it was kind of confusing what to do, but we've been seeing them a lot now. What's our first step? Divide. What? Right, and you can think of that too. So a half is going to equal e to the negative 0.087 t. And as many of these done, we can kind of skip some of this at this point if you're comfortable with that. What are we going to end up doing to find out what t is? Okay, so I'm going to take the natural log of a half and divide that by negative 0.087. And I'm okay with you skipping that stuff. Once you see these and you get better with them, there's not going to be as much work, and you know what's going to happen. So what you see the nearest, let's go 100. Okay. So approximately 7.97 days. Does that seem valid based on the last answer? Yeah. Before we found like, what was 9 days, there was like 40-some grams left. So it makes sense for 50 grams, it's going to be a little bit less than 9 days. All right. So that's it. We're going to look for today. Like I said, I'm going to go ahead and cut this about like half the section. So here's your assignment. You got not very many problems at all. I just picked out the ones that model what we did. The examples that we did were actually the even problems. So they're going to look exactly like these. So shouldn't be too much up with it. So what are you going to do? How are you going to be on?